All right, so here's the second half of section 10.6, and really you just have a couple examples left to go over. So now a different type of problem that we can do is to find a polar equation for the conic with the focus at the pole. So here I even told you for number 34, they even say it's a parabola, and then they tell us that the eccentricity is equal to 1. Well, great, they probably didn't have to tell us both things. And we have a directrix at y equals 1. What I find to be really helpful with this is to just draw a sketch, and it doesn't have to be great. But if we draw a sketch of this, if we have y equals 1, here would be our directrix at 1. And we have to have a focus at the pole, which it says in the directions, and that's part of it. We always have a focus at the pole. So if we know those two situations, or those two things, we know that our conic can never intersect the directrix. And we also have, we know that this parabola, then it's going to have to go right through the middle of this at 1/2, and it's going to have to open down like this. Well, that little sketch actually helps us to do a lot. So we can start off and we can sit with our polar equation. So r is equal to, we need our eccentricity, which is 1. We need our distance, and remember our distance is from the focus at the pole to the directrix, so that's also equal to 1. And then it's divided by 1. Now we have to determine whether it should be plus or minus. Well, because I'm moving up, it's going to be plus. Or if you move to the right, it will be plus. And then it's our eccentricity again, which is 1. And now we have a horizontal line. And remember, a horizontal line, or horizontal directrix, means that it's going to be sine. So then there's sine theta. So that one's really easy. When we're done, we should clean it up a little bit. So we have r is equal to 1 divided by 1 plus sine theta. And there is our polar equation for our parabola, and with the focus at the pole. Well, obviously they're going to get a little bit more complex than that. For number 36, it's an ellipse. Tell us the eccentricity, great. And we have a directrix at y equals a -2. So I always draw that in first. So if y is equal to a -2, there is my directrix. Remember when you have, when we're drawing an ellipse, if our directrix is horizontal, our ellipse is going to be vertical then, they're perpendicular to each other. We have a focus at the pole, and really it's just going to look something like this, and we don't really care. It's obviously a sketch good enough. So we have r is equal to eccentricity, which is 3/4. The distance from the focus at the pole to our directrix, and it's always absolute value, so that will be 2. We need to have a 1. Now it's plus or minus. Well, if you're going down, it's going to be subtraction. Our eccentricity is 3/4 again. And again, we have a horizontal line, so that is sine. To clean this up a little bit, I guess how I would start is say if I multiplied these two things together, in the numerator I would have 3/2 divided by 1 minus 3/4 sine theta. And you cannot leave a complex fraction. So I'm going to multiply the numerator and the denominator by 4. That's my greatest factor there, so I can get rid of everything. So if I multiply by 4, that will end up giving me in the numerator 6. In the denominator, if I distribute, I would have 4 minus 3 sine theta. And you do have to do this step. You cannot leave a complex fraction for your answer. So those are pretty easy. Moving on to number 40, we have a parabola. And now instead of telling us about the directrix, we know that we have a vertex at 5 pi. And we also obviously know that we have a focus. Our focus is at the pole. So here's our focus. If our vertex is at 5 pi, okay, pi will go this way, so I'll just put 5 here. There's my vertex. I know I have to go around the focus. So it'll look like that. And then with the parabola, we know that if that's my 5 from my focus to my vertex, I'd have to go 5 more to to the directrix here. But I do think that sketch is incredibly helpful. So now r is equal to eccentricity is going to be 1 because it's a parabola. The distance that we have, in this situation, remember, it's from your focus at the pole all the way to the directrix. So in this situation, it's going to be 10. And then that's divided by 1 minus, eccentricity is 1. Oops, I didn't say why we have minus. It's minus because our directrix is to the left. So it's 1, that's minus, now this situation. Eccentricity is 1, and now because I have a vertical line would be x equals, and x represents cosine, so that's cosine theta. And that gives us 10 divided by 1 minus cosine theta. The last one is a little bit more complex, so that's why I put another example in here. Oh, excuse me here. All right, so we have an ellipse, and it tells us where our 2 vertices are. So again, just to sketch a picture of this, I have a focus at the pole, and I have vertices at 2 pi over 2. So okay, pi over 2 would go up. Here would be 2. There's 1 vertex point. And I have another one at 3 pi over 2, and then or 4, 3 pi over 2. So 1, 2, 3, 4. There's my other. And remember, your vertices are always on your major axis, so it's going to look, it's probably going to be thicker or wider than that, but it would end up being horizontal. So then I know my directrix is going to be up here. Remember, your directrix is always closest to the foci at the pole. Well, we have a couple things that we have to figure out in this situation. When we write our equation, so we have r is equal to, we need our eccentricity. Well, we know that that's equal to c divided by a. And in this situation, to calculate c, the c, remember, is the distance from your center to your foci. A is the distance from your center to your vertex. So if we look at this situation, our entire major axis, the length of it is 6. So we know that our center will be right here. Therefore, C, the distance from your center to your foci, is going to be 1. And A, the distance from our center to our vertices, is going to be 3. So now we have our 1/3. Now we need D, the distance from our foci to our directrix. And really, I have no idea what that is right now. I just drew in a directrix, so I don't know that. But so I'm just going to say, well, that's D. Then I have divided by, it has to be a 1. My directrix is above the pole, so I'm going to add to it. Eccentricity is 1/3. It's a horizontal line, so that's going to make it sine theta. Well, we specifically have to know what that exact distance is. And one way of doing this, in order to figure out what D is we can plug in a point that is on our ellipse, and that can help us solve for D. So, to solve for D, plug in a point on the ellipse or any conic that you have. Well, they gave us 2 points because our vertices have to be on our conic, so I'm going to use the point 2 pi over 2. And if you used 3 pi over 2, that would work just as well. All right, so that means I have 2 is equal to 1/3 times D divided by 1 plus 1/3 sine pi over 2. When I calculate this, sine of pi over 2 is equivalent to 1 times 1/3 is 1/3 plus 1 is going to equal 4/3. I'm going to write a whole step out here. So I have 2 equals 4/3 is in the denominator, and I have 1/3 times D in the numerator. Well, now, depending on how you want to solve this, a couple different ways. You could cross multiply right now. You could simplify your complex fraction right now. It really doesn't matter. The other thing, you know that both of these have a denominator of 3. So those two things basically just simplify out. So I'm going to use that and say, all right, I know that this right side is equal to 1/4 times D. Therefore, D is equal to 8. So this directrix is really moved way, way, way up here compared to what my drawing actually has. And now when I rewrite my equation, if D is equal to 8, I would have 8/3 divided by 1 plus 1/3 sine theta. And now I'm going to multiply everything by the numerator and denominator by 3. So my final answer here is going to be 8 divided by 3 plus sine theta. So keep that in mind. When you don't know that distance, you cannot guess it. You can figure out your eccentricity. Great. From there, plug in a point that is on your conic, and that will allow you to solve for D. All right, last one is Kepler's law. This is named after the German astronomer Johannes Kepler. And each planet moves in an elliptical orbit with the sun as their focus. So for our example, we have Halley's Comet has an elliptical orbit with the sun at one focus, and eccentricity is equal to 0.967. The length of our major axis is 35.88 astronomical units, and we have to find a polar equation for the orbit, and then we also have to figure out how close does Halley's Comet come to the sun. So we have two things we have to solve for. A, find a polar equation. B, how close does Halley's Comet come to the sun? Well, we can really draw this however we want. It really doesn't matter. As long as we come up with a formula for it. It doesn't matter if you make your ellipse horizontal or vertical. Either answer would work for this. But here's the sun, and the sun has to be a focus is what they told us. So Halley's Comet has an elliptical orbit. The sun is one focus point, so that's our sun. And I'm just going to have mine look like this, which means I would have to have a directrix over here. And again, like I said, you can draw this vertical if you want to. Or the ellipse can be vertical. You could have your directrix over here. There's really 4 different scenarios on how we could set this thing up. What we do know is that our eccentricity is approximately 0.967. We also know the length of our major axis. So remember, wherever our center is, the length of our entire major axis is 2A. So 2A is approximately 35.88. Well, then that does allow us to solve for A. So if we take 35.88, 35.88, divide that by 2, 17.94. So that's the information that we have, and we have to find an equation, a polar equation for the orbit. Well, to get started with this, I like to start with my formula and fill in what I can. So I know my eccentricity is 0.967. This D again, this distance, I really have no idea what it is, so I'm just going to say D for now. And then I know in my denominator, I have 1. My directrix is to the right of the pole, so I have to add. Eccentricity, 0.967. And I have my directrix is vertical, so that means it would be cosine theta. Well, very similar to the last problem, I have to figure out a point that I can plug in. So I have to find a point that is on my ellipse, and I don't know that right now, but obviously with the information that was given here, I can find it. So basically, if we look at this, we know that A is 17.94. So that means from here to here is 17.94. I really just want to figure out, what is this value? Well, I can do that by figuring out what is this A value, and I can find A because I have, this C value, which is the distance from your center to your foci. And I can do that because I have the eccentricity and I have A. So remember, eccentricity is equal to C divided by A, which allows us to set up the 0.967 is equal to C divided by A, 17.94. Therefore, we know that C is approximately 17.94, which I already have in there, times 0.967, and that gives me, I'll round to 3 decimals, 17.348. 17.348. Well, if this is 17.348, I know that's very small, and then A is equal to 17.94, I can find this distance. So if I take A and subtract C from it, I'll have that distance, which will tell me the coordinates there. So if I take A, 17.94, 17.94, and subtract A, just kidding, A, subtract C, which is 17.348, now I have 0.592. And that is this distance, this red distance, which I want because now I know what this point is. So I know that this vertex point, I'm just going to call it P, a point that is on my ellipse, is 0.592. So when I go and plug this in now, I have 0.592 is equivalent to 0.967D divided by 1 plus 0.967, and then I have cosine 0. Well, cosine 0 is 1 times 0.967 will give me 0.967 plus 1. So therefore, my denominator is 1.967. I'm going to multiply that over. So I have 1.967 times 0.592. So I know that this side is 1.164. That's equal to 0.967D. I can solve for D very easily. So divide it by 0.967. D is, I should say approximately, 1.204. And now when I go back and rewrite my equation, R is equal to 0.967 times 1.204. That is divided by 1 plus 0.967 cosine theta. And then if we multiply together, I guess that would be nice to do here, we can say that our equation is equal to 1.165 divided by, so I multiplied the 0.967 times 1.204, and then divided by 1 plus 0.967 cosine theta. So there is the first part of our question, which was lengthy to get to in order to figure out what is that point, but given the eccentricity and the length of our major axis, we can solve for that. Well, we had 2 questions here. The second, so we found our polar equation. The second question, how close does Halley's Comet come to the sun? Well, this is going to be our closest point, and remember, here is the sun. I'll try to enlarge this a little bit. So this is our closest point, and we already found what that distance is. Remember that what the heck am I saying here? We calculated this distance as this A minus C. I got to get it on the screen. A subtract C. And so we had the closest that it gets is 0.592 astronomical units. So that would be our closest distance, 0.592 astronomical units. All right, well, that's the end of chapter 10. which is kind of nice. There's the three big ideas in this, the polar part of it, the parametric part of it, and then dealing with conics back in section 1. So it's kind of nice, I guess, to have another chapter done under our belts. And homework for this section I don't think is it's pretty good. Most of the examples we've gone over. So if you get confused, I did put the numbers in the notes so that you can go back and see where things are coming from. And then you'll review and take a good old test over chapter 10. Good luck.